In this lesson, I'm going to introduce the concept of a tangent and a secant. Now both tangents and secants are defined with respect to some function. Therefore, we're going to start by drawing on a graph and some function on it. So first we'll start with the definition of a secant. A secant is just a line drawn between 2 points on the graph of a function. Now before we go ahead and find the equation of a general secant, let me go ahead and do a specific example first. So suppose I defined a function f of x and gave you its graph. Suppose we wanted to find the secant through this graph that cuts the x-axis at x equals 1 and 3. Now to actually find the equation of this line, we're going to want to start by actually finding the coordinates of these points on the graph. We can do this by substituting their x values directly into the function to find the y coordinates. So I just fast forwarded this, but I started by subbing in 1 into the equation, so I replaced all the x's for 1's, and then when I put it into the calculator, I got the number 4. This means that the first point is at 1, 4. After this, I then replaced all the x's for 3's, and then when I subbed this into the calculator, I got the number 8. So this means that the second point is at the point 3, 8. Now that we have two coordinates, we have to remember that 2 points make a line, and therefore we can just treat this like we're finding the equation of a line between 2 points. To begin with, I'll go ahead and choose some general points on the line, x, y. Now I'll go ahead and label the points we were given, a and b, and the point that I chose can be called p. So I just want you to remember that in order to get the equation of a line, the gradient between a and p has to be the same as the gradient between a and b. Now things are looking a little bit cramped, so I'll just go ahead and move some pieces out of the way. Now to find the gradient for AP, I'll draw a triangle beneath a and p. Now the width of this triangle is just x minus 1, and the height of this triangle is just y minus 4. Therefore the gradient between AP is just the rise over the run, so it's just y minus 4 divided by x minus 1. Now to find the gradient between a and b, we should also draw a triangle between a and b as well. Now the width of this triangle is just 3 minus 1, so it's just equal to the number 2. And now the height of this triangle is just 8 minus 4, so it's just equal to 4. And now this tells us that the gradient between a and b is just 4 divided by 2, which is the same thing as the number 2. Now if we just go ahead and move the x minus 1 over to the other side, and then we move the negative 4 to the other side, we now have the equation of the secant between the points at x equals 1 and 3. Now that you can see how we do a specific case, let's do it in the most general case as well. Just like we had in the example, I'll go ahead and label the x values a and b. And we also know that the coordinates of the points a and b are a f of a and b f of b. To get the equation of this secant, we pick some random points on it with a coordinate x and y. So we want the equation of the secant. Just like we did in the example, we can say that the equation of the secant is given by equating the gradients between a and p with the gradient between a and b. Now we can find the gradient between a and p by drawing a triangle beneath a and p. Now the height of this triangle is just y minus f of a. And the width of this triangle is just x minus a. Now this just means that the gradient between a and p is just y minus f of a divided by x minus a. And now we can repeat the same process for a and b. Let's start with the triangle below a and b. Now this time the height is given by f of b minus f of a. And the width is just given by b minus a. And because the gradient is just the rise over the run, the gradient between a and b is just f of b minus f of a divided by b minus a. Now we can go ahead and actually rearrange this formula by multiplying both sides by x minus a, just like we did in the example. And then we can go ahead and move the f of a to the other side and swap it for a plus. And now this equation that we have is just the equation of a secant between a and b. So now that we've finished discussing what secants are, it's time to talk about what a tangent is as well. In order to properly understand a secant, I just want you to imagine that we had a car driving along the direction of the function. As you can clearly see, the car is not facing the same direction as the secant we drew. In fact, even if you were to actually move the point B, you can actually never draw a secant that goes in the exact same direction that the car would be facing at this moment. In a sense, this actually gives us a great definition for what a tangent should be. You can say that the car has the exact same gradient as our curve at this particular point A. Now this point that I've drawn on here is the tangent, and in a sense, it has the exact same slope as our curve at this particular point A. Now, unlike a secant, a tangent only needs a single point to be properly defined. If I was to bring back our car from before, I want you to imagine that we've taken a photo of the car at this specific time. In a sense, the tangent captures the direction that this car would be moving at this instant in time. Therefore, we call this the instantaneous direction of the car. Now, let me go ahead and give you a simple example where we can actually find the equation of a tangent. Let's pretend that we had the parabola x squared minus 4x plus 5. Now let's imagine for a moment that we also had the line y equals mx that goes through the origin. Now as you can see, y equals mx cuts f of x in these two places. Now let's imagine reducing the gradient so that y equals mx touches at only one place. So as you can see, if we pick the exact gradient for m, the function and the line are going to touch at only one place. For this value of m, this line over here will be the tangent to this graph f of x. So let's increase the gradient again so that it's hitting the curve at two places. Now to solve for the required gradients, we actually want to find the x-coordinates where the line and the graph intercept. Now, if we remember that the graph is given by y equals f of x, we can equate y equals mx with f of x. Now we can go ahead and move the mx to the left-hand side. And then we can factor out a minus x from this middle part over here. Okay, so now looking at this equation, we have a quadratic to solve, so we should use the quadratic formula. To begin with, I'm going to break this part up into two fractions so that I have this plus minus in the middle. Now I'm going to label the parts of the quadratic a, b, and c. Just keep in mind that a is just equal to 1. Now because we know that a is just 1, let's just get rid of every a in the quadratic formula. Next we know that c is 5, so 4c is just 20. Now finally, b is just this minus 4 plus m over here, so negative b is just going to be 4 plus m. So now if you think about it, this xm over here is just going to be the same thing as 4 plus m over 2. This is because we start at the middle, and then we add something, which is this whole term over here, and then we subtract the same thing to get to these other two roots, x plus and x minus. So if we want y equals mx to only hit the curve at one place, then we have to add and subtract 0. And that means this part on the inside of the square root should also be equal to 0. So to solve this equation, we just move the 20 to the right hand side. Then we just square root both sides to get rid of the square. Now finally, we have to move the 4 to the right hand side to get our final value of m. So that means when m equals root 20 minus 4, the picture is going to look a little bit like this. Now since m is just root 20 minus 4, then the equation of this tangent is just y equals root 20 minus 4x. And now, because we said that this part over here would be xm, we could just sub in root 20 minus 4 to find xm. So we can also go ahead and sub in m equals root 20 minus 4. And then we can go ahead and cross out the 4's. And this immediately tells us that the tangent hits the curve when x equals root 20 over 2. Now as you can see, finding the equation of the tangent this way is actually a fair bit of work. So let's get rid of this example to talk about how we might go about doing it in general. Now the function I gave you in our example is actually a very simplified case, and it's actually quite rare that we can ever do that to find the equations of tangents. Now it turns out to find the general equation of a tangent to any function at all, we're going to need to go ahead and learn a little bit of calculus. So therefore, to find the equations of tangents to general functions, we are going to need to cover a bit more material. So to quickly summarize this lesson, we said that secants are just lines drawn between 2 points on a function, and tangents are, in a sense, lines that have the same slope as our function at some particular point. And with this, we've actually completed our discussion on tangents and secants.